Hi, this is Mr. Ward, and welcome to another Circles Geometry video from Chapter 10, Section 2 on congruent chords. In this video, I'm going to talk about problems 11, 12, 13, and 14. Let's start off with number 11. As I have counseled you before, please consider the problem yourself before seeing how I do it. Try to solve it yourself. I'll give you some hints and some thoughts about how to break down the problem, but then you should pause the video and see what you can take care of on your own. You can come back after that and see what I did. So, number 11. In number 11, we are given a circle, Q. That means Q is the center of the circle. And we've been given that QM is congruent to QN. We're also told that QM is perpendicular to TP or PT. We're told that QN is perpendicular to UP as well. And we want to prove that PR is perpendicular to TU. So let's label the things that we've been given. We've been told that QM and QN are congruent. So that's useful to know. We've also been told that they are perpendicular to TP and UP. And that tells us by Theorem 68 that UP and TP are congruent. Now, that tells us that P lies on the perpendicular bisector of UT because P is equidistant from the endpoints of UT. So see what you can do with that. I've probably given away too much. Pause the video and then we'll continue. I got excited about that one. So let's go ahead. I assume you paused and you figured it out yourself and now you're back. So we know that P lies on the perpendicular bisector of UT, but do we know that PR is the perpendicular bisector? Well, to figure that out, it would help to find another point that is equidistant from U and T that lies on this segment that is PR and on to S. So let's do that. We can very easily do that by drawing a radius from Q to U and also from Q to T. Those radii are congruent because it's a circle and Q is the center. And so Q also is on the perpendicular bisector. And if you have 2 points that are equidistant from the endpoints of a segment, then you have determined the perpendicular bisector. So PQ and also PR then are the perpendicular bisector because R is on the segment PQ. So if PQ is the perpendicular bisector for TU, PR is definitely perpendicular to TU. Okay, now let's consider numbers 12, 13, and 14. Let's talk about 12. 12 is circle F, so F is the center of the circle. We know that DB is congruent to EC, so DB is congruent to EC. And we also know that FDB and FEC are right angles. So there we go. So think about what our theorems tell us about this. We're trying to prove that AF is perpendicular to DE. So to prove that AF is perpendicular to DE. So to do that, you're going to need to use your perpendicular bisector theorems in addition to the congruent chord theorems. So go ahead and pause the video and let's see what we can figure out about this. Well, one thing we know, assuming you've paused the video and you're back now, one thing we know is because DF is perpendicular to DB, we know that DB is congruent to AD because D forms a bisector, and DF is a perpendicular bisector of that. So we also know that EC and EA are congruent because E is a midpoint, because EF forms a perpendicular bisector with AE. But since we know that DB and EC are congruent, we may as well extend the congruency all the way from D to A, because we can just add congruent parts to get a congruent sum. So now we know that AB and AC are congruent. Okay. So, but what's really important in this situation now is that we can establish a couple of points that are equidistant from D and E. One, we can establish that A is equidistant to D and E because of segment AD and AE being congruent. But we can also establish that since AC and AB are congruent now, that F is equidistant to D and E as well, to those chords. And so now we know that F and A are equidistant to the endpoints and therefore determine the perpendicular bisector for DE. So we are set with that one. Now let's consider 13. 13, we have circle O, so O is the center. We know that PQ is congruent to TS, and we're trying to prove that RQ is congruent to RS. Okay, so let's consider things that we know. So let's label things we know. Let's start with that. So PQ and TS are congruent. That's the only thing we've been given. But that will give us some stuff that we can use. We can use Theorem 69 to work out some other components that are going to be congruent. And then we can go from there. Now, I'm going to ask you to pause the video and we'll see what we can do. All right, I hope that you have paused the video, and now I'm going to start drawing some segments. I'm going to draw the distance segment from O to TS and the distance segment from O to PQ. And those distance segments form a right angle right here and right here. Okay. And now I'm going to form, actually, let me use a different color. Use a different color for that because, cool. All right, we're going to use a different color for this. I'm going to use blue. Actually, first, let's name a couple congruent things. So we know that those distance segments, perpendicularly bisected, PQ and TS. So that's useful to know. And we can draw an additional segment. Let's make it purple. We're going to connect O to R. And OR is itself. So it's congruent to itself. The distance segments, the equidistant segments from O, are also congruent. So we've got a hypotenuse of a right triangle, of two right triangles that's shared, and we've got these two distance segments that are congruent. And since they're right triangles, we can use hypotenuse leg to prove that O R, whatever we're calling this, I'll call it A, and I'll call this B. So we'll say OAR and OBR are congruent by hypotenuse leg. And if that's true, then we can use Kappa to prove that BR and AR are congruent. And since those are congruent, then by subtraction, we can say, let's pick a new color. We'll use yellow for this one. It's not the best option. We'll say that SR and QR, RQ and RS are congruent by subtraction. Okay, cool. Let's take a look at 14. I'm going to have to move the screen a little bit for number 14. So we got more stuff on here to consider. All right, so let's look at what we know. We know ABC is isosceles with AB and AC being congruent. So let's label that information. We'll use green. So AB and AC are congruent because it's an isosceles triangle. Okay, I've covered up F there, so I'm going to draw F so we know that it's there. All right, this is circle E. So E is the center of the circle. And we know AD is perpendicular to BC. We know that EF is perpendicular to AC. And we've been told that AF is a measure of 6. So let's label that. That's a measure of 6. And we've been told that ED is a measure of 1. Okay, so we want to find the radius of the circle, and we want to find the perimeter of triangle ABC. So pause the video and see what you can come up with. So this one is going to require some systems of equations and a little Pythagorean theorem and maybe some quadratics. But let's identify a couple things we know. We know that if AF is 6, then we also know that FC is 6 because EF is perpendicular to this segment, so to this chord, so that we know that this is 6. And so we can say, of course, that AC is 12. That'll be useful for us. Now, the next thing we could identify, we could do, is we could draw another segment. Let's draw this segment here, EC. Okay, now that's a radius, and it's going to be congruent to EA. And since one of the first thing we want to find is the radius of the circle, let's label that radius R. Okay, call that R, and that's R. Okay, now what we've just done is we've set up parts of a right triangle. So AD is going to be R plus 1, and AC is going to be 12. Now let's go ahead and give DC a label as well. We'll call that Y. Okay. I don't know what we're going to call it Y, but we're just call it Y. Okay. So what I'm going to do is I'm going to go ahead and go to text mode because that works a little better for me than actually, yeah, I'll do that. So let's drop the point size to something a little smaller. Okay. So here's what we've got. We know that we've got two triangles that we can deal with. So one of the triangles we can deal with is this tall one, ADC. And so let's organize an equation for ADC. And the other one we're going to do is EDC, which is also right. And the nice thing is they both have a side that's y, that's going to be y. So for the tall one, we know that 12 squared is going to equal r, radius, plus 1 squared plus, oops, okay, then plus y squared. Okay, the next thing we know, oh, looks like I have to go back over here. So we also know that, let's see, we know that for the other triangle, for the smaller one, that r squared equals 1 squared plus y squared. And we're going to rearrange these so that they both equal y squared. So what I'm going to do is I'm going to rearrange this to be r squared minus 1 squared. And over here, I'm going to rearrange this to be 12 squared minus r plus 1 squared. I'm subtracting that from both sides. So now I have two equations that equal y squared. Oops. Okay, so they both equal y squared. Now, since they both equal y squared, they equal each other. Okay, so now I can bring them together. Drop this because I don't need it anymore. And we can start solving for r. Okay, so we don't need the y anymore because all we really want right now is r. Later on, we can figure out what y is from knowing what r is. So we will need y for the perimeter. Okay, so r plus 1 squared is going to be r squared plus 2r plus 1. So we can drop that squared now. Okay, that's minus. So this is, of course, 144. Okay, and that's going to be minus r squared minus 2r and minus 1 because I dropped the parentheses next to a negative. And over here, I've got r squared minus 1 squared. So what I'm going to do now is I'm going to, let's add r squared to both sides. So that's going to be 2r squared. Let's add 2r to both sides. So that's plus 2r. Okay, I did not mean to drag that all over there. Let's move this back over. Okay, hopefully it'll let me go back into text. Yes, it does. Good. Okay, and then this is minus 1, so that's just minus 1. And since minus 1 is on both sides, we can cancel it. And then we can subtract 144 from both sides. So that'll equal 0. 2r squared plus 2r minus 144. And then let's divide everything by 2. So that's going to be minus 72. That'll be 1. That'll be 1. And now we can factor this and have it equal 0. And then we'll be able to solve for r. So when I factor this, I need two factors of negative 72 that add up to 1 because the coefficient of my middle term is 1. So what are two factors of 72? Of negative 72, I should say. Well, 9 and negative 8 will do the job. So we could say r plus 9 and r minus 8. And if that all equals 0, then r could equal negative 9, which we'll discard because we want to have a negative 9 radius. And r could be 8 because 8 minus 8 would be 0. So we now have r, the radius of this thing. Okay, radius equals 8 units. Okay, now that we have that, we can figure out the rest. So if we know r is 8, we know this is 6 plus 6, so that's 12. We also know that the other side of this thing, let me go back to this. We know the other side of this is also 12. And now we can use the Pythagorean theorem to figure out what y is, because that's going to be y, and that's going to be y as well. Those will both be y. I think I want to use a different color, so get rid of that. Okay, we'll go back, grab that tool, go to there. So the base is y, so we just need to find out what y is in order to figure out the perimeter, because that's the other thing we need. The perimeter of this is 12 plus 12 plus 2y. All right, we know this radius is 8. we know that this is 1, and this is the hypotenuse. So we can do our next little equation, like a little Pythagorean equation, for just this triangle here. Okay, so we know r is 8, so we'll say 8 squared. Okay, and that's going to equal 1 squared plus y squared. And so that's going to be 64. And that's going to be 1. So we're going to subtract 1 from both sides. So that'll be 63. Okay, and 63, we're going to need to get the square root of both sides. So the square root of y squared is going to be the square root of 63. So square root of 63. Now 63 is 9 times 7. And we can get the square root of 9. We'll pull that out. That's going to be 3, plus or minus 3, but we're not going to want the negative. So it's 3 root 7. Okay, so I'm just going to, y is 3 root 7. So this here is going to be 3 root 7 on the right and 3 root 7 on the left. So we put that all together, and this side is going to be 6 root 7. 6 times the square root of 7. So our perimeter is 6 root 7 plus 24. 12 plus 12 plus 6 root 7. So I'll type that in here. The perimeter is going to be equal to 24 plus 6 square root of 7. And that is that. All right, I hope that was helpful, and I'll see you later.